Hey guys, here's the third day of 6.1. This time we're going to essentially rotate our graphs and we're going to be finding the area along the y-axis. So instead of having a function that is always above and a function that's always below, we're going to be looking to see is there a function always right and a function always left. So most of the time in this section, equations are going to be presented with either x's and y's on both sides of the equal sign, or maybe it's going to be an x equals equation instead of a y equals equation. A lot of the times with these problems, the graph is going to be given because you can't always graph it on your graphing calculator. Desmos does a nice job of graphing it, but your regular calculators may or may not. Okay, so just as a warm-up, this is the same type of problem that we did earlier in the week. There are three equations here. We're going to graph all three of them, and we're going to find the area bounded by the curves. Okay, so I'm going to go to Desmos and graph x square root of x minus 2, negative x square root of x minus 2, and just wash up, and x equals 4. Alright, x equals 4. Okay, so x equals 4 is just a vertical line. So it's sort of like having a limit of integration. So we can see the space that we need. It's basically the bounded space between the red top function and the blue bottom function. Okay, the green line, and then right here, essentially the vertices of both red and blue. So our limits of integration go from 2 until 4. Our top function is red, and our bottom function is blue. So x square root x minus 2 minus negative x square root x minus 2 dx. Okay, so then we end up having really minus a negative or plus a positive. So 2 to 4, 2x square root x minus 2 dx. Okay, that can go into our graphing calculators. This is essentially what we graphed, and that's the space where we are looking for. So remember functions, miscellaneous integral 2, 4, 2x square root x minus 2 dx. So 12.07. Okay, so this was a problem where we had a function that was always above, a function that was always below, and we had a left and a right limit of integration that was numerical. X's were inside, x values were on the integral. Okay, so remember that when we first started this idea of area between a curve and the x-axis, where the positive and the negative area was. And this was simply when there was a single function, not two functions like what we're doing right now. But we talked about how area up here was positive, whereas area down below was negative, right? We had problems like this. Anything below the x-axis was negative. Same idea. When we flip it, right? When we flip it to the y-axis, space on the right is positive, space on the left is negative. Now this again is for a single function. The reason when we do it for two functions, you're always going to get a positive answer is because you're looking for the distance between two functions. And you're always picking the higher function, aka the bigger function, or the function that's further right, and also that yields a larger value. So a right minus left number on a number line or a top minus bottom number on a number line would always give you a positive. Okay? So this is really just for visual purposes. Our answers in this chapter will always be positive. Okay? The important thing to note now, though, as we move into this next section, I'm going to model a few in a second without doing them from start to finish, is if our equations are in the integral as respect to y's, then we have a dy in there, and our letters are our numbers, our limits of integration, c and d in this case, are y coordinates. Okay, so in this example we would go from -6 up to +6 as our limits of integration. Okay, so let's take a look at a picture. This is an example that we could do in both directions. I could say to you that the red graph, the root x, is always on top of the blue graph. And I would do this problem as I had before. And I'm just going to set it up with language. So red minus blue, because this is top, minus bottom, and therefore that's a dx. And therefore I pick the number as x values 0 to 1. Right? Or I can change the way I think. I can say, what about if I rewrite these equations? So I would have to say this is equal to x equals y squared, right? And I would have to say that this is equal to x equals the cubed root of y. Those are equivalent. Then I could say, well, blue is always further right than red. And now I'm working horizontally across my graph. So this blue graph is a bigger value than the red graph. So then I'm thinking blue minus red, or right minus left. And if I do this, it's a dy. And therefore, I'm looking for top number and bottom number on my y-axis, 0 to 1. Some of these problems I can do in both directions. Sometimes I have to do it one way versus the other. So the question you're saying to yourself is, do I have a right-left scenario, or do I have a top-bottom scenario? Generally, the way that the equations are presented to you will help you decide which way to do it. Because this equation was presented to me originally as a y equals, I would have naturally picked the first method. If they presented it to me as x equals, then I would use the second method. So let's take a look at another one. Okay, right here. My red, it's like a sideways parabola. It's presented as an x equals. I would have to do some work in order to isolate. I also can't say that I have a function that's always above and a function that's always below. Let's take this example right here. If I look right at this moment, isn't red on top of red? So therefore, I don't have a consistent top and bottom scenario. But I do have a consistent right and left scenario. Right? So if you were to take your pencil horizontally and move it up and down the graph, the pencil, I wish I could show this to you more effectively, but the pencil is always anyways, I can't show it to you, I wanted to. But the pencil is always touching blue on the right and red on the left. That makes this a much more convenient right minus left, which is a dy integral. And therefore, I would pick limits of integration that are y coordinates, -2 until 4. The only work that I would have to do is make this an x equals, which would be y minus 1. If you're doing right minus left, only y's can be inside the integral. If you're doing top minus bottom, only x's can be inside the integral, so you have to be consistent. Okay, here's a right minus left. This parabola, I don't have the equations, but there's my right, and there's my left. From the y value of 1 up until the y value of 3. Okay. All right, so these were just visual examples. Let's actually walk through first the notes, and then we'll walk through some problems start to finish. So you're going to still graph the functions on the same coordinate plane. Again, sometimes they're given, sometimes it is something that you can graph, either through Desmos, or you might have to rewrite it to y equals to get the graph. Find the intersecting points, but the difference is we need those y values. Determine, I don't like this language, some people still do, determine which function is right and which function is left with the respect to the y-axis. This will be right and left, so it's there. I just want to make sure you fully see it. And then we integrate with respect to y. So here's our first example. Find the area of the region bounded by, let me change colors, x equals y squared plus 1. Right, that's our red parabola. Okay. Y equals 2, y equals 1. These are horizontal lines. They're really nice because they're actually our limits of integration. It's the same idea as if they said from 1 to 2. Okay. And then the last thing is we're also bounded by x equals 0, which is really just the y-axis, the vertical line at 0. So the space that we're finding the area of is right here. Okay. So now, in that space, in that blue highlighted space, we have our right bound, which is the curve. We have our left bound, which is the y-axis, or 0. We have our upper limit, which is 2, and our lower limit, which is 1. You're always finding a way to box in the space, right? It's not obviously not a rectangle or a square always, but we are always going to satisfy the bottom, top, right, left scenario. If it fills in like I just did, that's a dy. If it fills in like this, it's a dx. Okay. So the last couple of lessons we covered the dx's, now we're covering the dy's. So let me circle the one that we're going with. So the right equation, notice if I have a dy, I need y's in there, which is great because it's already solved this x equals y squared plus 1. So my right equation is y squared plus 1. My left, I don't really have to write it, but it's 0. It is a dy, and I go from 1 until 2. Now, people that are using regular graphing calculators, 83s, 84s, you don't have to type y in. You could still type it in as x. On your paper, I would write it down as y so you don't get confused. But on your calculator, when you type in this integral, just use the variable x. It's the same thing. So I have y squared plus 1 dy. On Desmos, I'm going to use a y. I think. I shouldn't say that so confidently. 1 to 2, parenthesis y squared plus 1 dy. Yes, I can. So 3 1/3, 3.3 repeated. Okay? Now, could I have done the other way here? No, not really, because the changing side is this curve, right? So if I said, oh, the top is 2, the bottom is 1, well, then my right limit of integration, well, that changes all along that parabola. So this was an example where I have to use right minus left. I have to use dy. Okay. All right, here's another example. Find the area of the region bounded by x equals y squared minus 1 and x equals y squared minus 1/8 y to the 4th plus 1. So they're graphed. We need our y coordinates that are points of intersection. We need the right and the left, not the above and the below. And we're going to integrate with respect to y. So the graph is very detailed. We can see the shaded region. We can see where those points of intersection are at. I'm okay with you trusting this graph. Right, but it's important that I'm picking y values. I'm not trying to pick x values here. The equations are already solved. Maybe you're looking at it like, what if I didn't know? What if it wasn't labeled so well? How would I know which one is the y squared minus 1 and which one is the y squared minus 1/8 y to the 4th? Well, right there, that 4th power should indicate to us, if we're looking at, it's really like a sideways polynomial, I have more turning points. The x equals y squared minus 1, that's basically a parabola. So that one is the pink, the y to the 4th one is the blue. So what is further right? Well, at any given moment inside of this space, right, the blue graph is on the right side from the pink graph. So blue minus pink is always our right minus left in that whole space from bottom to top. What did I just write? Right. And this is a dy. So in equation form, it goes from -2 till +2, parentheses, two sets, y squared minus 1/8 y to the 4th plus 1 minus quantity y squared minus 1 dy. Now this is one that I'm definitely going to simplify because the y squareds actually cancel out. -2 to 2. So y squared minus y squared. We have a -1/8 y to the 4th. 1 plus -1 would be, 1 minus -1 would be 1 plus 1 or 2. Okay, so -1/8 y to the 4th plus 2. So -2 until 2. So negative division bar 1/8 y to the 4th plus 2, parenthesis, dy. 6.4. Okay. Okay, a couple more. Okay, so I'm going to graph these on Desmos. If you're graphing them on an 83, 84, what you would have to do, now again, I don't recommend it. You all have access to Desmos. It makes it a lot easier, but if you wanted to graph it on your graphing calculator, you would have to take this and solve it for y. Right, so I'm solving with a square root. What do I have to remember when I'm solving with a square root? Plus and minus. So I'm actually graphing both the positive root x plus 5 and the negative root x plus 5, and I would do the same thing for my other equation. So keep that in mind if you're graphing with a graphing calculator. In order to get the full picture, for this problem, you're actually graphing 4 different functions. So x equals y squared minus 5. Let me clear this out. Okay, so x equals y squared minus 5. Okay, there's one of the parabolas, and x equals 3 minus y squared. So there's our space, our points of intersection we need, right? We need the y coordinates, not the x coordinates. So those y coordinates go from -2 until 2, green minus blue. Right, green is the second equation that I graphed, blue is the first. So integral, -2 until 2. Green was 3 minus y squared minus y squared minus 5, using parentheses, dy. So 3 plus 5, that's an 8, negative 2y squared dy. Okay, 21 and a third. Okay. All right, go ahead and give this one a try. You have a red line and a green parabola. The points aren't very clear here. Points of intersection, remember, you could set these two equations. I'll do that as side work for you. Set these two equations equal and solve. So when is y squared minus 4 equal to 2 minus y? I'm getting -3 to 2, integral of 6 minus y squared dy. It was red minus green. $20.83. Did I skip one? Yep. All right, last one, you guys. Okay, graph given, both as x equals right minus left. The line x equals y is on the right. The parabola y squared minus 2 is on the left. Our job is to figure out what are these points of intersection in terms of y values. Okay, so setting y squared minus 2 equal to y equal, treating it as a quadratic, right, setting it equal to 0, factor, so y equals 2 and -1, so that's -1 and that's 2. So we go from -1 until 2, line minus parabola, dy. Okay, so y minus y squared plus 2 inside that integral. -1 to 2. -1 to 2, parenthesis, y minus y squared plus 2. Parenthesis, ty. 4.5. Okay. Hopefully you found these lessons to be helpful. Again, 3 days per section is what we're going to do. So that worksheet that is already posted is your assignment for the next E-Day. So today's E-Day, which is the 17th, is just to watch this video. Go through, understand, take notes, prepare yourself to be ready to complete that worksheet on the following E-Day, and then I will post a quiz later next week. And then the following week, we will start 6.2 with the same exact structure. All right, if needed, I can absolutely set up office hours, so just let me know. I can set up a Zoom, even if you just want to say hi. All right, guys, take care.